Okay, so next set that we're going to take a look at. The force required to stretch a Hooke's law spring, basically that means a spring like we're using in class. Technically they're called ideal springs, but for our purposes it's all the springs that we're going to take a look at. A good comparison for what is not a Hooke's law spring is the lab that we did. When you all saw the rubber band, its graph didn't look so good, wasn't really a straight line. That would be an example of a spring that isn't one that follows Hooke's law, at least for what we're using. All right, Hooke's law spring, so spring like we're used to. The force required to stretch it varies from 0 newtons to 51.6 newtons as we stretch the spring by moving one end 5.88 centimeters from its unstressed position. Find the force constant of the spring, which is a different way of saying the spring constant. That's what we've talked about in class. What they're saying is we've got a spring, and it starts off with 0 newtons being pulled on it, and it has a natural length of, let's see, they don't actually tell us what the natural length is. Just call it L. And then they say they start pulling on this. You can imagine that we have a small block here, and that they start pulling on the block, and they stretch this out where it comes all the way out to here. And we've got this distance, 5.88 centimeters. And they say that basically what they're doing is they're pulling on it. They've got a force in which they're pulling this way. That they started at 0, and they started to pull harder and harder, as we saw in class. You have to pull harder and harder to stretch the spring out. And when they got it 5.88 centimeters away, the force that they're pulling with is 51.6 newtons. When I draw a free body diagram of the edge of that spring, I would actually put a block on there, but we're going to ignore things like friction. We're looking only in the x direction. You could imagine that it's on a frictionless table, for instance. But we've got a force that they are pulling with that is equal to 51.6 newtons. And we have a spring force that is trying to pull it back this way. The spring wants to return to its natural length, so it's going to pull back this way. Well, if I'm pulling this thing out here and then holding it there, then when I do my sum of forces in the x direction, it'll be equal to the pull force minus the force of the spring equals my mass times my acceleration in the x. Now, I didn't give you the mass of this object, but I told you that I'm pulling it out there and just holding it. So that means that our acceleration is actually 0, so the mass doesn't matter. I can add the force of the spring over here, and we find that the pull force must be equal to the spring force, which is also equal to 51.6 newtons, because that's what our pull force is. Now we know the spring force. So my spring force is 51.6 newtons, at least that's the magnitude. And to be technical, it's actually to the left, so I put a negative sign here. Equals, let's go ahead and put that in. I told you that technically the force of a spring is equal to negative k delta x. The negative is because whichever way you move the object, the displacement, which is a vector, the force will point the opposite direction. We have a force to the left, so I'm going to say that my F, my force, negative 56.1, negative because it's to the left, is equal to negative k delta x. If you forget the negatives in this, it's not the end of the world, but keep in mind sometimes you might end up with a weird result. These equations technically are supposed to work with these negatives. A lot of times you can go through and say, okay, 51.6, the magnitude is just equal to k delta x. If you're not paying attention to direction, you could ignore the negatives because they're all about direction. Technically, my force is to the left, so I'm going to put a negative here, and that's what that negative actually ends up dealing with. So we've got negative 51.6 newtons equals negative k, my spring constant, times delta x, my displacement. Now here's where the direction is important. Displacement is a vector. If you remember, I've taken this and I pulled it to the right, so my displacement is positive, and it's a positive 5.88 centimeters. Now we're doing math, so we want to do things in SI, so 5.88 centimeters becomes 0.0588 meters. I would divide both sides by negative 0.0588. Basically, my negatives cancel out, and let's see what we get. So I get 51.6 divided by 0.0588, and I end up with, if I've done this correctly, my spring constant, which is what this problem is actually asking for, is 878. It's 877.55. But I'm getting 878 newtons divided by meter, Newton per meter, which is the standard unit for a spring constant. All right, let's see. So this is, yep. In fact, the answer is 877.551. They got exactly my value. Okay, so that's the first part of this one. Let's take a look at the next one. They want us to build off of this. They say, find the work done in stretching the spring. Now, here's where things get a little bit tricky. On this one, you can technically find the work done stretching the spring. But for the most part, you can't do it the way that you might think. If we use our work equation, F delta x cosine of the angle between them, technically those guys are vectors. Our problem is our force isn't just one number. Now you may be thinking, well, put in the 51.6 newtons, except remember, it starts at 0 and then climbs through a bunch of different numbers until it gets to 51.6 newtons. Which means my force is constantly changing, which means technically, if you wanted to solve this, you would have to use this equation instead. Do not panic. This is calculus. It is not something that most of my physics classes are working with. If you happen to be an APC student, you should actually be able to do this. Although, I'll save you some time, you're just going to end up finding what we've found before. Take a look at one of the other videos that I mentioned. There's more than one way to solve for work. Work is a change in energy. More specifically, it's the final energy minus the initial energy. Well, I can solve this doing the same thing. Work equals my final energy minus my initial energy, also known as delta E. It's not simply a change, although many times you can call it that. Well, the types of energy that I'm dealing with here are actually just the spring potential energy. It moves a little bit, but at the beginning it's not moving, and at the end it's not moving, so its kinetic energy is going to be the same in both cases. I don't have it go up and down at all, so that means that we don't have a change in gravitational potential energy. So what we're looking at is our potential energy stored in the spring. We started off with no energy stored in the spring, so if we can find out how much we have in it at the end, that's the work that we did, because we're the ones adding that energy into that spring system. So in this case, our work is going to be equal to our final spring energy, which is 1/2 K delta x squared, minus our initial, which is 1/2 K delta x squared. Now I might want to mark this as delta x1 and delta x0. My initial stretching and my final stretching. Now the initial stretching is actually no stretching at all. We started with the spring at its natural length, so there was no stretching. My initial delta x is 0 meters. My final delta x, however, is 5.88 centimeters. So let's take the values that we had from just a moment ago. We found 1/2, and just a moment ago we found that my spring constant was 878, I believe. Yep, 878 newtons per meter times my extension at the very end, which is 0.0588 meters, quantity squared. So I'm going to take 0.0588 squared times 878 divided by 2, and I find that the new energy that it has, my energy stored in the spring, comes up to 1.52 joules. Newton divided by meter times meter squared. One of the meters cancels out, and we end up with Newton times meter, which in this case is actually a joule. If I've done this correctly, we find that the new energy stored in the spring is 1.52 joules, and it came from me stretching it out, so that's got to be the energy I transferred into it. That should be the work. Let's double check. They found 1.517, which would be 1.52 to 3 significant figures. So we should be good. Once again, Don't think that just because I'm asking for the work, you have to use the work equation. There are a couple problems where you have used the work equation. Sometimes it's the best option to use. But sometimes, if you know more about the energy, what you want to do is remember that work is a transfer of energy. So if you have your energy changed, that's done by work from some source. It's adding energy or removing energy. That is a really powerful thing to keep track of, not to be confused with power.